today, we will start Part C, Role of Data Structures in Algorithms, Part C.1, Search Unordered Arrays. So in this part, we will have a new topic, mainly about the data structures. Our main focus is on algorithms, but we have to consider data structures. First, I'd like to give you a simple computing problem, very basic computing problem. Search an unordered array. Our problem number 2. Given an unordered array, so we use this way. The indices from 0 through m-1, so total n elements in an array. And a search key k. We have a search key k, but you need to find an index I for which k equals a of I. So that is the problem. Search problem, the basic search problem. Here, in this problem, first, that is the basic problem type search. There are 3 different basic problem types for this class: search, sort, selection. Search, sort, and selection. We will spend a lot of time in these 3 types of problems. Today, we start the first one, the basic search problem. All right. The data structure we will use array. Also very simple data structure array. The reference for this topic you can find in section 2.1, page 47. All right. First, let's look at the importance of data structures in algorithm design. So what's the role of it? So in general, the reason that we use special data structures, so sometimes we need to use special data structures. The reason of that is we can make the data well organized. If we do not use special data structures, we do not organize the data. So data just in a unordered, random type. Without well-organized data, you cannot take advantage of the special structure of your data. Then some advanced algorithms cannot be applied. In our module 1, we do not have some stronger examples to explain this issue, but later we will, when we learn some other advanced data structures, so you will see the importance of the data structures. All right. So then our algorithms can take advantage of the structures and get a better performance. But for this viewpoint, here in this video, this part C, you cannot get very strong impression on it. So we need to delay this topic when we go to the advanced data structures. All right, but let us start with relatively simple example. So we have a lot of things to learn in the simple example. First, let's do analysis. Solving this problem is very simple, so you can solve it easily. Here, let me just quickly go through the basic solution. then we have discussion on it. The basic operation, we are going to use comparison. Comparison, yeah. And not addition, not multiplication. So from now on, you will see the main operation we are going to use comparison operation. Yeah. All right, yeah. The most commonly used operation for this class. So that is the comparison operation. Yeah. All right. How do we compare? Very easy. We compare k and element a of I. Yeah. And we start from the first element when I equals 0. Yeah. Then we do comparison in this way. Yeah. When we compare these two numbers, there are only two cases. The first case, k equals a of I. The two numbers are the same. In that case, we find a solution. So the program just returns that index I and stops, terminates. Your program terminates after a solution is found. Yeah. But the second case, k not equal to a of I. We know although there are two cases, right? K less than a of I or greater than a of I, but we combine them. Here, we do not need to know it is a less than case or greater than case. It's not important. Yeah. So we put them together. So not equal, that means we should look at the next element. Yeah. So we do the remaining operations, iterations, in this iteration way. Yeah. Then we compare k with the next element, a of I plus 1. Okay, yeah. And then we have two cases to be considered. Yeah. So we already discussed these two cases. So we'll repeat that procedure another time. Yeah. Then we need to consider the termination case. Yeah. When do we stop? Yeah. All right. So because to terminate the program, if you find the solution, you terminate the program immediately. All right. So then another case, you can never find the solution, right? Yeah. Until you reach the last element, but you cannot find a match. That's possible. In that situation, your program would return I minus 1. Why I minus 1? The reason is very simple. We know I represent the index, right? Array index. And we also know array index can never be negative, right? Yeah. It's greater or equal to 0, the array index. But here, if you return minus 1, you know it is not a regular index. It has some special meaning. The special meaning is no match. You cannot find given key in this array. So you want to represent that meaning. Yeah. It is a commonly used method. Very simple. Yeah, but it solves the problem. Yeah. All right. So now, after that, after you use that -1 special index values, then you can cover all the cases. Yeah. All right. So next, for this algorithm, there is a name for it. Sequential search or linear search. Yeah. So these two names, some people prefer linear search. Yeah, probably linear search is used more frequently. And some people like to use sequential search, you know. Yeah. All right. So next question. How do we measure its performance? Performance, or in this class, we also use this word, efficiency. All right? Yeah. Performance is the old way people call it, performance. The new way people call, the same concept, the people call efficiency. Okay? Yeah. So you will see, these two words used, different places, but you just treat them as the same meaning in this class. Yeah. All right. So next, let's do analysis. Yeah. So in our analysis, so let us count the number of comparisons. Yeah. Here, it's pretty easy to count for this problem. Very easy to count. Yeah. Here, let me do a chart here. So you can see when k equals different element, the number of comparison needed is different. Yeah. The first element, if k equals the first element, only one comparison, it is enough. Yeah. Second element, a of 1, 2 comparisons, and so on, okay? Until you get the last element. But there is another case, no match case. After you compare the given key k with all the elements in the array, still no match, you need n comparisons. Yeah. Here we cover all the cases. Among all the cases, you can see the first one is the best case. So you use the minimum number of comparisons. So the first one is the best case. Yeah. The last two cases, the worst case. Yeah. So worst case, a little more complicated. There are two different cases correspond to the worst case. Yeah. All right. Yeah. But our next question, how to measure the overall efficiency? Yeah. Because in the real world situation, most of the time, people like to know the overall efficiency of certain algorithm. Yeah. So then we need to understand that concept. What do you mean overall efficiency? Right? Can you use the best case? No, you cannot use the best case because it only represents a special case, the best one. So you cannot use that to represent the overall efficiency because you are too optimistic, right? If you use the best case, you are too optimistic. Yeah. The same reason you cannot use the worst case. Yeah. Because it represents the worst efficiency, right? So if you use this worst case for the overall efficiency, you will be too pessimistic, right? Yeah. Just opposite of the optimistic. So pessimistic. Yeah. That's not good. So it's not good. Too optimistic, too pessimistic, right? Yeah. So you should consider all the cases and represent all the cases in a fair way. In a fair way. So that's the case we need. Yeah. Yeah. So the measure should include all the cases. And, represent all the cases in a fair way. Yeah. So what do you mean fair way? Yeah. Average. Using special average, we will have a fair way. Yeah. All right. So here, the question, how do we know all the cases? Yeah, so this is another questions, sometimes not very easy to see. Yeah, here it's simple, so I can show you. How do we get all the cases? Yeah, we need to make some reasonable assumptions. Yeah, sometimes we need to make some reasonable assumptions, just like in our first problem, we made some assumptions about multiplications, additions, right? Unit of time needed. Yeah, but here we need to make another assumption. Yeah. All right, so let's look at assumptions. Yeah. For all these cases, so you can see these cases happen with some probability concept. Yes, yeah. But our first assumption is the first n cases. Yeah. So we call the hit case. Yeah, hit. Yeah. Because you find a match, you get a hit, right? Yeah. Hit case or match case. Yeah. So we can consider that. Match case or hit case. Yeah. Okay? Yeah. So in the match case, hit case, each of the element, we assume they have the same probability. Same probability, yeah. So K equals the first element, the second, the third, any of the element in the array with the same probability. So that is a reasonable assumption. Yeah. So that's the first assumption. Yeah. But the second assumption, now we need to consider the no match case, and sometimes people also call the miss case. Miss, it's not a hit, it's a miss. Yeah. So no match, that probability we need to know. Okay? Yeah. So we make that our second assumption. Yeah. So this time for the index case, so that's all the match case, hit case, the index case, we assume the probability is P, with this P between 0 and 1. Inclusive, yeah. 0 also possible, 1 also possible. Yeah. Then the -1 case, I equals -1 case, then its probability is 1 minus P. Because you only have these two cases. The total number of probabilities equals 1. Yeah, based on our knowledge in probability. Yeah. All right. Yeah. So with these two assumptions, next we can do the analysis. Yeah. All right. So in our second video, we will do analysis using these two assumptions. Yeah. All right. So let me stop here for the first video.